Hello everyone, welcome to this class, Organic Spectroscopic Analysis. In previous lecture, we have learned about X-ray photon-electron spectroscopy. Do you know where binding energy shifts come from? Or how can we identify elements and compounds? When a beam of X-rays is directly to a sample, the interaction between an X-ray photon and the core level electron of an atom causes a complete transfer of the photon energy to the electron. The electron then has enough energy to escape from the surface of the sample. This electron is referred as to photon electron. Elements have unique electron binding energies. Therefore, knowing the electron binding energy allows the identification of various elements. XPS is thus able to detect all elements except hydrogens. Furthermore, the electron binding energy is also sensitive to the electron environment of the atom. When an atom is bonded to another atom of an element having a different electronegativity, the electron binding energy may increase or decrease. This change in binding energy is called the chemical shift, which can be used to provide chemical information of a molecule or compound. The exact binding energy of an electron depends not only upon the level from which photon emission is occurring, but also upon the formal oxidation state of the atom, the local chemical and physical environment. Changes in either one or two give rise to small shifts in the peak positions in the spectrum, so-called chemical shifts. Such shifts are readily observable and interpretable in XPS spectra. Atoms of a higher positive oxidation state exhibit a higher binding energy due to the actual Coulombic interaction between the photo-emitted electron and the ion core. This ability to discriminate between different oxidation states and chemical environments is one of the major strengths of the XPS technique. In practice, the ability of resolve between atoms exhibiting slightly different chemical shifts is limited by the peak widths, which are governed by a combination of factors, especially the intrinsic width of the initial level and the lifetime of the final state. The line width of incident radiation, which is for traditional X-ray resources, can be only proved by using X-ray monochromators. This resolving power of the electron energy analyzer. In most cases, the second factor is the major contribution to the overall line width. This is an example for the spectrum of the oxidation state of titanium. Titanium exhibits very large chemical shifts between different oxidation states of the metal. In this spectrum, we can observe a shift to higher binding energies with increasing oxidation states. Electronegative oxygen binds the electron more strongly. What are the applications of X-ray photon-electron spectroscopy? 4 examples of XPS analysis of pigment. For mummy artwork, XPS analysis showed that the pigment used on the mummy wrapping was lead oxide rather than iron oxide. For the analysis of carbon fiber, polymer composite material by XPS. XPS analysis identifies the functional groups present on the composite surface. Chemical nature of fiber polymer interface will influence its properties. This is an example of analysis of materials for solar energy collection by XPS depth profiling. The profile indicates that reduction of the tin oxide occurred at the interface during decomposition. Such a reduction would affect the collector's efficiency. Okay, for this lecture, we have talked about the spectrum, chemical shifts, and applications of XPS. Thank you for watching.